Hi, everybody. How are you doing? Welcome back. We'll start in a few minutes. Let's check out your assignment and notes.
Hello.
Hi, how are you doing?
Good in yourself?
I'm good, thank you. We are getting ready to go over chapter 4. So if you can take a look at your notes and your assignment, we'll do that together.
No problem. I printed them out.
All right, thanks.
Hey, Professor Glenn, I had a quick question.
Yes.
Just so I kind of have a better understanding of assembly, is assembly like the foundation of a program? Like, let's say Microsoft Word, is that like the backing to have that happen?
Yeah, so for assembly language is often used to build compiler, browser, working with drivers, directly with hardware. So you can build regular programs with assembly language, but in some cases on the I/O level, for example, like your smartphones, you will likely need to, the developers, they program some of the instructions for things like turning on devices and things. Writing libraries can be useful with assembly language. So when you're working with boards and also building compiler and browser, you will likely work with assembly language, or when you're working with IoT devices. Now, we often teach the higher programming language, but in computer science, you have to understand how the processor works. And there are jobs that require, assembly language like ARM, Microsoft ASM, etc.
Wow. Jeez. Okay.
Yeah, so if I see those, I previously worked with DoD companies, and one of the companies, they hire specifically ARM developers to work with some of the smart devices, the automated devices that they use for jets and other types of military base equipment. Yeah, so you can find work in that require assembly knowledge. Often that you would see more jobs in development with Python, Java, C++.
Okay.
Yeah,
Thank you.
you're welcome. All right, so we're gonna start in about a minute. I'm gonna go ahead and share screen. Let me make sure my screen is. So if you just got in, make sure we look at the notes for this week, which is chapter 4. We are going to do an assignment on von Neumann model and assembly language. So we are going to get a little deeper into data movement and the model and how things move from the different parts of the processor, looking at different registers. And then in the lab this week, we are going to work with numbers. So you will see a little bit more on how to use the simulator better, to really look at memory addresses and work with memory addresses. We do have a homework assignment, which is a quiz 1 review. So take a look at that, make sure that you go through the questions, complete the assignment by Sunday, because we will have a quiz next week and I will activate the quiz game. The highest score will get a gift card for Amazon, of course. So take a look at chapter 4 notes for now, and we're going to go over the assignments. Do we have any other questions before we start? Okay, so let me get my notes going. So before I dive into the notes, I just want to share with you a little slide that I done a while back when I started teaching, intro to computer and also assembly especially. So I just want to give you a little overview on how things have changed over time, because we are going to talk about von Neumann model today. And just to give you a little bit of history on how things has changed since 1940s. Okay. So just to start, in 1937 through 1942, the ABC was one of the first few computers that were created, and that was from Iowa State University. And just to give you a little bit of the background on that, it was using just vacuum tubes. And all of these systems, keep in mind that we use them to do arithmetic calculation. And this is why you still see the structure, the architecture being developed, as we need more computational power and also different purpose for computation. But the computer is really a calculator. And so here you can see a picture of it. It's 300 vacuum tubes. It was created to compute algebraic equations, and it weighed about 320 kilograms, so pretty heavy. And it was pretty large. And so this is a picture that was taken from the History Museum. So you can see how that would look like. So that was one of the first computer, or the first few computers that you see. And you probably heard of the Colossus, and Colossus was used for encryption. This is one of the earlier encryption machine, and it takes up like it was a room size. It was able to use actually 5,000 different characters per second. So we saw this in 1943, and that was used for encryption purposes. So that's what the Colossus looked like. And then later on, the replication of it, as you can see, this is still existing in some computer museums. So if you get a chance to visit, you will be able to see. And this is from University of Pennsylvania. There's a website that's dedicated to ENIAC. And so in 1946, UPenn, John Eckert, Mulkey, and their associates, and on the website now start recognizing some of the women that contributed to this particular project. So ENIAC was a system that used 36 vacuum tubes. So we went from 300 vacuum tubes down to less vacuum tubes. And it used triodes and flip-flops. So you start seeing some switching components inside the system. Okay. And then this picture captures the grandfather of computing system, which is John von Neumann. This system was created from 1947. It was later released in 1950. He was the first scientist that really built the system as what we see today, where it would have memory for storage. And that was from there, we will be able to write software program and applications. But it also have processor, and the processor consists of control unit and arithmetic logic unit, which is what we will talk more about. And back then, while the storage is small, but that was really used to store information and instructions. And so later on, this architecture is still being adapted. So this is what you see in your modern computing system, and von Neumann model is still being expanded upon. So this is what you see, and that's his picture on the left. Okay. And then UNIVAC came out in the late 50s, and the team that previously created the system modified the system and created what you see with the UNIVAC one. And this was actually for a government project as a research project with the university. So it costs about $1.5 million, and 46 systems were built and delivered. It was, again, used for basic calculations and computations. And then the UNIVAC 2 was a later model that transitioned from UNIVAC 1. And from here, we started to see that we can implement text. And because of von Neumann model, we were integrating memory and storage. Now, this system weighed about 16,000 pounds, so approximately 8 tons. And as you can see, the instructions were limited. The word size were limited. There were only 54 instructions used. So when you're looking at the modern processor, our modern processor is able to handle a lot more instructions, especially when it deals with hardware components that is outside of the processor itself. And there was only one address. So we'll talk about the number of addresses in the ISA architecture today. And the instructions to be decoded was about 54. So it was somewhat limited, but it was definitely, a transformation from what we've seen previously. Okay. So that just to give you a little bit overview on how we had transitioned our system from the 40s to the 50s, and now what we have is in the 2022, our system is definitely a lot more advanced, but we still revert back to the original model. So coming back to the notes, we started to define what instructions are and what a computer program can be. And as most of you are studying computer science, you have been writing computer programs. So when you write your computer program in any languages, it's really a set of instructions that allows the computer to execute task or a certain well-defined piece of work. And that can be carried out through functions, or you can integrate that in the main when you're looking at C++ or Java. Now, breaking it down from the higher language to the low level, you started to see the low level instructions in this class when we talk about add and in some assembly language, we would see or, move, rotate, etc. LC3 gives you the basics. And so if you grasp the concept, learning additional or different type of assembly language is very simple. So when you're looking at instructions, it's really a smallest piece of work that is specified in your code or your program. So we can simply add a number, right? We can use instruction to add the 2's complement, or we can do other things like output strings, as what you've seen in the last lab. So in 1946, John von Neumann proposed the foundation of what we use today, which consists of 5 parts, and make sure we know this for our exam and quiz. So the 5 parts are memory, which is what you've seen in RAM, and currently we're using VRAM along with regular RAM like DDR4. So that is more on the temporary storage. And then we also have storage that is more permanent, consists of hard drive or solid state drive. And you also have external storage. So we have expanded the storage area, but ultimately your system, your computer system, must have memory. So RAM. And so whether you look at a Raspberry Pi, or if you're looking at your regular PC or your MacBook, it still requires RAM. Then it needs to have a processing unit, and this is where your processor comes in. And so with the processing unit, it would have 2 elements. So I'm going to scroll down a little bit so you can see. And so what you see when we're using the register 0 through 7, that's really a temporary storage area inside the processor. And from a consumer standpoint, we see this, being displayed as cache, where you would have a certain size of the temporary storage to be able to process some information. And as we use some of the registers, we would see that the temp storage is being integrated. And then you also have the ALU, which is Arithmetic Logic Unit. And this is used for your operators. This is used for computation, like adding. So with the processor, you would have the processing unit here. Now, the computer is no good if we don't have any form of input or output. We want to have interaction with the computer. So you would have input devices like keyboard, mouse, and scanner to enter the data. Now, some device it's both input and output. For example, your all-in-one device like your printer, scanner, copier, one of those that you buy so you can print out your homework and scan your homework. That's an I/O, right? You can input data by scanning it in, and you can output data by printing it out. Your hard drive or your SSD, it is an input and output. You can extract data from it, and you can store data into it. Also, DVD burner, Blu-ray burner, those are more on both sides. But when we're looking at specific input, we have to find a way to enter the data into the system, right? For game, for computation, for calculation, for word processing, whatever it is. Then we have to have some output devices, things that we can see right now, your screen, your monitor, your printer, your LED, right? And also your disk, your external drives, that's also both, okay? So because of von Neumann model, we're still using, right, the architecture, the way it was designed, okay? Now, there also is a control unit that exists in the processor, and that allows the system to control which instructions to execute, which instruction is going to be next, and how it's going to look at instructions. So after, right, it is going through the control unit, then we can compute, which is when we calculate, and we will be able to move things across the registers. So this model is now still being integrated. And so here I give you the breakdown for each of the definition, right? Your memory store data, processing unit performs arithmetic and logic instruction, therefore it has ALU. Control unit interprets instructions and control what the instructions is going to go next. And then your input, we need to transfer the data into the system. And output, we want to extract data from the system. And your data only exists in memory, right? It quickly goes through the processor, but ultimately it's going to store in your storage. Okay, any question? Okay, so let's switch over to our assignment now. Okay, for number 1, we need to describe the components of von Neumann model or the machine. Okay, so you often hear it's referred to von Neumann model or von Neumann machine. So as we can take what's on the notes, we can specify what the memory does, right? It contains instructions and data. The processing unit, it performs arithmetic and logical instructions. So in the case where you're writing an if statement, or when you're having, when you're implementing, operators like not is not something, right? That ALUs handle that in the processor. You have the control unit, which interprets the instructions. So when you program in C++ or Java or Python at the high level, right? That really is going to be broken down to the low level instructions. And the control unit coordinates and also interprets the instructions. Then you have I/O, so input to bring data into the system, and output to transfer data from the memory to your device. Okay, like your monitor, your printer, etc. So any questions on number 1? Make sure we know these. And we're going to come back to some of, these elements down the line, some of the components. Okay, so before I explain number 2, you saw that I put a lot of red notes there, but let's look at your notes. Okay. So now we're going to look at the memory. So the way that we visualize this in your simulator for the lab, right? You would see memory addresses and then the instructions at the memory address. This is why you originate at a certain address. That's where your program is going to start. So basically when you code .org, right, a hex 3000, what you're doing is just telling the system that your program is going to start at the address 3000. So what it's going to do is going to put all your code, which include instructions, at each of the subsequent addresses starting at hex 3000. Now, we also need to think about memory as an array of addresses, where these are the array actually contain bits. And so when you purchase RAM or storage, right, you often hear the word bytes, whether it's megabyte, gigabyte, terabyte, or petabyte. That's the largest, right? The next large container. But so when you're looking at a byte, that's really 8 bits. And when we work with assembly, especially LC3 or for ISA architecture, your word size is going to be 16 bits, so 2 bytes. Okay. So when we're looking at 256 megabyte, which is fairly small nowadays, right? Back then, that will be very large. That will contain 2 to the 28th power of your address space. So that means that it has that many addresses. So if I take my calculator and I calculate 2 to the power of 28, I would get 268,435,456 different addresses. So that's the address space for 256 megabytes. Okay. So the way that we identify this, that will be that you would have unique location. That will be the number of bits. And in LC3, we would see that that will be 16 bits, right, for each of the location. And so if we can also group them together to have multiple locations would be allocated for your array or a group of data, right? That would require more than 16 bits. And so your content that will be a certain bit value that will be stored depending on your data. Okay. So then we would then think about when you're allocating storage, and we want to make sure that we effectively and efficiently use our storage. This is why sometimes we would reuse certain area, or you don't want to take up all the storage space, right? So we have to think about how we can, write a function and then call that function or continuously reuse the functions. So that way we don't take up a lot of space. Instead of writing 5, right, function for the same thing, we can call that same function multiple times. Because as you write your functions in C++, at the low level from assembly standpoint, you're really taking up the storage to really include the instructions and the data that can be used in that function. Okay, so now in the next question of your assignment, it asks you if a system has 512 megabyte of memory, what is the maximum address space? So we know that it's going to be 2 to the n for the address space, okay? And so when we utilize a certain storage size, we can refer to it as log of 2 to the n bits for the address that will be referred to as the n bytes. So in the case of a 256, you can store values of 8-bit number, right? Because remember that scale that I taught you, because everything is in binary, that's why we use log 2 of n. But that scale that we learned, the least significant bits start with the 1, and then you would multiply it by 2, so 2 to the n power, right? So when you get to the 8th bit, you would have 256 as the equivalent decimal. So that means that there are 8 bits can be 8 bits that can address 256 bytes, okay? Now, when you go further on that scale, let's say that we need to convert this to kilobytes or megabytes. We have to multiply the bytes by the 1,000, and so that will be approximately 2 to the 10th power, okay? So when we say, kilobytes, that will be 2 to the 10th, okay? So you need 10 bits addressed for every byte in a kilobyte. And so if you want to go to the next level, which is the megabyte, you will need 20 bits addressed for every byte. And so when we're looking at gigabyte, you need 30 bits addressed for the gigabyte. And so that would be, so when you're looking at this value, 2 to the 32 power, that's going to give you 4 gigabyte. Okay. Any question? So now when you go back and think about the software requirement, right? Like your operating system, for those of you who use PC, you're familiar with this. Okay. When we transition to a different OS in Windows, right? Windows would have a certain requirement for the base of the OS. And it also have a ceiling for that operating system, right? For example, the 32-bit. The 32-bit in Windows 7 or Windows XP prior, right? Vista, right? The ceiling of that OS is 4 gigabyte for RAM, okay? That means that even if you have extra RAM, it won't be able to use it because it is a 32-bit, so it's only able to allocate this many addresses. So if you have a 16 gig RAM for a 32-bit OS, it's worthless for the rest, the 12 bits, the 12 gigabyte that you have put in. So it's only able to use up to the 4 gigs. Okay. Now, as we expand to the 64-bit, right, operating system, as we have supporting processor that supports 64-bit, that means that we can have 2 to the 64 power, right, of that number of addresses. So we now can scale out to our storage use. And this explains how we would think about our processor bit size and the RAM requirement to be able to execute instructions at the software level. Any question? Okay.
I have a good question, Professor. So is
Yeah.
is the memory dependent on the processor? Is that how it goes?
Yes.
Okay.
Because your address space, right, the bit size of the processor really translate to how it used the address space in RAM. So when you're using a 32-bit system, right, and you're using 32-bit OS, the software for that system, this is the maximum number of addresses that you can use because it's 2 to the 32 power. Mathematically, that's the max. Okay.
Got it.
So as now you start seeing system with 64-bit, you're able to use more RAM, right? And your processor now come equipped with different cores, so for multitasking purposes. So the question, coming back to the question, it asks you 512 megabyte of memory. How can we calculate the maximum of the address space? So I give you the breakdown here. So we're going to take the n, which is the 512 that we're given in the questions, and we're going to apply the log 2 of n. But because it's megabyte, we have to multiply that by 1024. This is for kilobyte. And again, multiply 1024 for megabyte. Okay. So when we say 512 megabyte, it's really 512 times 1024, and again times 1024. And we would use log 2 of that value. Okay. So if you use distribution, right, method across, you would have 9 plus 10 plus 10, because log 2 of 512 is 9, log 2 of 1024 is 10, and log 2 of 1024 is another 10. So we actually have 29. Okay. It can also be written natural log of, right, the n value, 512 megabyte, divided by natural log of 2, which still gives you 29. So if you punch into the calculator, right, you can do it this way, or you can do it this way, and you still be able to get 29. So that means that it's going to have 2 to the 29th power, right? Okay, that's the amount of addresses that you will be able to have with the 512 megabyte. So coming back to our calculator, let's clear this, and we will have to take 2 and raise it to the power of 29. Okay, so you would have 536,870,912 addresses. That's your address space. 2 to the 29th, or that value. Any questions? So we would have 29 bits, right, as referred to what we saw here. Okay, 29 bits. I should put that so it's clear to you. So the 29 bits address space. Any question? No question? Okay. All right. So now let's get into your memory operations. And you saw some of the instructions when we did the string output in the lab, right? And as you load that into your LC3 simulator and you click run, you notice that there's an LD, right? After you did the load effective address. Okay. So in memory operations, we would load to read a value from a location. So simply what happens is when you load, it places an address at that location. Okay. And that address is going to place in what's called the memory address register, your MAR. Okay. And then it's going to interrogate the computer's memory. And then the second step is that the information stored at that location, it's going to have an address. It's then going to place that address into the memory data register. So the data that's stored at that address, it needs to take that address to be able to put it onto the MDR. So when you declare a variable in C++, right, and you initialize that variable to a value, let's say I have int variable 1 is 4, right? So when that data is initialized, what happens is it needs to take the address for that variable and load it into the MDR. So later on, if you're using that variable it's able to know that 4 is the value, the data for that variable. Okay. So when you load, these are the 2 steps. So here it gives you an example. It says to load a location A, it's going to write the address of A to the MAR. So it's always going to use the MAR, right, for the address location. After that, it's going to send the read signal to the memory as it needs to interrogate the computer memory. Then it's going to read the data from the MDR. Okay, so the 4 that you initialize needs to be read from here. Question. So we talked about what load is. Now, next we're going to talk about what store is. Store is when you write a value to a location. Okay. So when you store, it's going to write the address of the memory location in the MAR, the memory address register, and the value to be stored in the MDR. Remember that MDR stands for memory data register. So the data is always going to go to the MDR. The address is always going to go to the MAR. Okay. And the second step is it's going to interrogate the computer's memory with the write enable signal. So it has to send that signal. And the information that's in the memory data register will be written into the memory location with the address in the MAR. And that's how it writes to RAM. So RAM simply in the memory that you're using, right, for your application, it simply is load and store. So the example here, it says, it tells you here that when you to store, if you store a value X at a location A, your data, which is X, is going to be written to the MDR, your memory data register. Then it's going to write the address, which is A, into the MAR. And that's how it's able to obtain the data when you use that in your code. Right? So after that, it's going to send the signal right to the memory. And that's how it writes data to RAM. And RAM stands for random, right, access memory. Question. Okay, so in the next question, it asks you, what are the 2 basic operations in memory? And we just went over that, your load and store. Make sure we know what load it does and what store does. Any question with 1, 2, or 3? So now, after the load and store section, it's going to get into processing unit or your CPU. So here, it states that your processing unit in our modern system would have complex functional units, right, to be able to compute for more advanced needs. But in the simplest processing unit, you would, from what we talked about with von Neumann model, it would consist of what's called the ALU, or the arithmetic logic unit. Now, the size and the quantity that's being processed by the ALU is referred to as word. So you can have 1 word, and in LC3 in this class, we know that 1 word is going to be 16 bits. So the ALU would then process 16-bit quantities. Okay. And the architecture we're using is ISA. So each ISA has its own word length, depending on what is used. Okay. So some architecture would have word size that would be 32 bits or 64 bits in the modern system. Okay. For Microsoft, as you saw with when you use the calculator, a word is 16-bit, right? And that really stemmed from the olden system, which is your 8086. So when we teach Microsoft ASM, right, we often refer to the Intel 8086. And the NASM, they would refer to also a similar architecture. So for this class, we need to know that our ISA architecture uses 16-bit word. Okay, that will be a question on quiz or exam. And for our registers, R0 through R7, there are 8 registers in LC3. Those are just small temporary storage of your processing unit. And they're in charge with operands and results for the functioning part with the instructions, right? So we use that to compute, and it's just temporary storing. So when you look at the simulator, if you look at the registers, right, after you run the program, it no longer stores some of the values, right? Sometimes you would look at certain register and it will have -1 as it completed the program. So for the next question on your assignment, that's pretty easy. We touch on that the word length in LC3 is going to be 16 bits. And the function for your registers in your system processing unit for number 5 is in charge of operands, results of the functional units. Okay, because we can add, right? We can add, values from a certain register, like R1, add with R2, right? And then store it back into R1. And 6, I think we saw in the diagram, we talked about this when we touched on von Neumann at the beginning of the lecture. So the example of your input, output device, and your I/O device. So your keyboard is an input device. And at the least, you would have some form of device to enter the data, whether it's going to be your virtual keyboard front screen, that's what you see on the smartphone, or you would have a real attachment with a hardware keyboard. Okay. And a mouse, touchpad, you can list other device there for input. Now for your output, we would at least see, right, text, numerical values, things that are displayed from our system using a monitor. We can also print out a hard copy using a printer. So those two are output devices. Now your I/O devices, we can name, that will be like storage drive, like your hard disk drive, your HDD, or SSD. That could also go for USB external drive and so on. And if you are dated like me, you would probably know about your DVD burner, right? So that will be your RWs. Or Blu-ray burner. So some devices can be used as input and output, whereas other devices like your monitor is only output. Now, a touchscreen monitor is input and output, right? We're able to touch it to enter, right? And, data you can, so your touchscreen on your smartphone is an I/O device. Any question with I/O? So in the next section on page 3, it talks about peripherals and it goes into keyboard, mouse, and monitor. And we're going to come back to this toward the end of the semester, but I wanted to go over a little bit because we can talk about data register on the keyboard and such, right? So each of the device would have its own interface. That means that it would contain a set of registers like MAR and MDR in your processor. So your keyboard is the supporting input device in LC3. That's how you're able to enter data, where your monitor would be the supporting output device in LC3. And in the keyboard, you have 2 types of registers. The first is going to be your data register. And the second register for the keyboard is the status register. And we'll expand on this later on. The same thing with your display monitor. It has a data register and a status register. It's known as the DDR for display data register, and status register is DSR. Now, as you work with devices, we know that each of the device, right, would have some form of driver. This is a program that controls access to the device. And in order to use the device, you have to have the driver installed. And most of the modern OS already have, right, the generic driver or the drivers that you would need, because it would be able to identify what type of drivers that is. And they have set a group of drivers that's built into the operating system itself. Now, if you're using a device that doesn't have the driver because it's unique, right, you can install the driver. Or if you're using a device that uses your OS driver and it doesn't work accordingly, like let's say a biometric reader, which is an input device, then you would need to update the driver. Okay, so driver simply is a program that controls device access. And operating system needs this so you can interact with the hardware, right, from the operating system standpoint. So when we're using the operating system, it allows us to access files, which is really stored in your storage device, right? When you're playing game, you're using your video adapter, your monitor, your keyboard, all of these input and output devices, and it needs that driver through your OS to be able to give you access to these devices and capitalize on the functionality of these devices. So going back to our questions, you already saw this for 7, right? Device driver is a program that control access to the device. Next, we're going to talk more about our processor. And here we're going to focus on the CU. So control unit really orchestrate the execution of the program. And when you're looking at the simulator on the top right-hand side, right, you would see PC and IR. And that's part of your control unit. It coordinates right? What's being executed, and it interprets an execution or instructions for execution. So what does the IR do? Okay. In order to keep track of instructions that's being executed based on what you have written in the program, the CU uses the IR to contain the instruction. So the IR really contains the current instructions. Okay. Now it's also keeping track of the instruction that's next. So it has a register to store what's in queue or what's gonna be executing next. And this register is referred to as a PC or a program counter. And here the author notes that because of the legacy system, they use the term program counter, but it really should be used to be, it should be called instruction pointer. So this register really point to what is next instruction to be processed. What's next in queue. Okay, so that's what your PC really is that it's going to keep track of what's coming up, whereas the IR it's storing what's current with the instruction. Any question? Now with the control unit really, its purpose is to do these things. To read an instruction from the memory. Okay. So when we say instruction, what does that really mean? Right? In assembly level, something like LEA, R0 and the label, or add R1, R2. And when it reads the instruction from memory, it's really looking at, it's going to have the instruction address in the PC, in the program counter. It's only going to use the address at the PC. Now, when it interprets the instruction, it's going to send the signal to the components on what to do. Okay. And so the instruction may take one cycle or many cycles to be complete. And usually it would take many cycles to complete. So your control unit really coordinates, right, the execution of the instructions, what's current and what's next. It also sends signal so that way it can interpret. As it interprets the instructions, it would send signal to the components. Now, when you issue the in assembly, right, what that is it's really waiting for the keyboard to be input. So once the user strike a key, what will happen is your keyboard sends a signal to the processor and say, hey, right, there's a character that's being entered. Okay. So now it's going to also set up what the instruction is next, which is going to be on how it's going to take that input from the register 0 and be able to do something with that, right? Like as we put that into the code. So as we have the user input the data, what we're doing with the data is what's next in queue, and that's the address is going to go to the PC. Okay, any question on CU? So leaving this class, you should have a good understanding on what the processor does and how at the low level, the processor, how it's handling instruction. Even though ISA is the simplest architecture and LC3 is like the simplest assembly language to learn. But if you're thinking about like Snapdragon and, your Intel i9 or your AMD Ryzen 9, etc. Right? Processor, the way that we design it hasn't been changing too much as far as how it's handling instructions. Just sometimes different architecture would require different instructions, right? Additional instructions. Some are going to be similar to what you've seen in LC3, but ultimately you have the CU and the ALU in the processor temp storage, which is referred to as cache, and then you have RAM to work with the processor. So now we can take what we talked about from our notes from chapter 4, right? For question 8, it asks you to describe the control unit components and their purposes. So I simply put that it keep track of the instruction to be executed. The control unit has the instruction register, which contains the current instructions known as the IR. Second, to keep track of the instruction that's what's being processed next, it uses the register that contains the next instruction address, which is known as the PC or the program counter. And you can find this also on our notes. So when it processes instruction, the program and your data is stored in sequence bits in the memory. And so when it execute it's going to execute one instruction at the time. And we would see that with the simulator top down, right? So as you saw last week, when we did the lab, when we have LEA R0, right? HW for hello world. And then the second string that we put, so after we load it, right, we out it. So we display it, so it loaded and then output. And then we load another string again, and then we output again. So as we see that, what it's happening is that your data, right, and your instruction is stored in sequence of bits in your memory. And it's able to execute that, right? And so coming back to what we just talked about, the CU coordinates on how the instructions is being, what is current and then what is next. So an instruction really is a fundamental unit of work. And at the low level, right, it could be load, it could be store, it could be move, it could be, and in LC3, we don't use move, it could be rotate, and like I know Microsoft ASM does that. And, or it could be and. Okay. So fundamental unit of work. So when you're writing a function in C++, right, it needs to really break it down to instruction at the low level in order to execute it. Okay. And your compiler handle all of this when it compiles and builds your program. So the three basic kinds of instructions that we see. Computational instructions, that will be add and not. And in other languages, we would see or, right? But for us in LC3, we would see these add and not. Your operators and your add, because it only adds. Your data movement instruction, we would load, store, and in LC3, we would load indirect. We would load effective address. We would store to register, and we would load to register. And we will expand more on this in the next couple of weeks too. You will know the specific. And when you are looping or when you're writing conditional statement, like for example, in C++, I can say if, right, A is 4, then do this. Okay. In assembly, we use a jump or a branch. So when you apply a condition, it can branch for yes or no. Okay. And in assembly for LC3, we can branch for positive, negative, or 0. Okay. And you will see how to do this. So we can also, when you implement a for loop, we will also branch, right? Because as we count down the loop, right, we would reduce down to eventually 0. And when it gets to 0, it's going to go to the next. So control instruction is really being utilized from a viewpoint of a higher level language is when you write conditional statements and iterative statement or loops. Okay. You can also do a jump, which is where you can send, right? You can send from your code to a certain section of your program. So it can skip some section and then come back to it. And you do see some of this where in some languages, it also uses label. You can go to the label. I know Java does that too. Okay. So control instructions allows you to control how your program will flow, right? Whether it's continuously executing that section or it would go to a different section. So for the instruction for processing, first, it needs to fetch the instruction from the memory. Now, this is why we start with the address of origination because we put everything onto memory. After it fetches it, it's going to decode it. And I know that you've learned this in all your programming classes because we talked about it repeatedly in computer science, but make sure we know these steps. Because as you understand each of these steps in this class, it's going to make so much more sense why you're doing certain things in your program in different languages. So it fetches the instructions from the memory, then it's going to decode the instructions. Then it's going to evaluate the address. Then it's going to fetch the operands from the memory, and that could be labels, data, right? Then it's going to execute the operation. Lastly, it's going to store the result. Okay, so fetch the instruction, break it down, look at the address, right? Fetch the data, right? And then execute and then store. Lastly is store. Sometimes in assembly, we will store and restore because when you have a change of data, you have to restore. Okay, like when you are when you're updating your variables or when you overloading your functions and so on. So not all the phases are needed by every instruction, of course, right? Depending on what you would incorporate in your code, but overall you would see these steps. Okay. All right. So with that, we can answer the next one. Number 9. For instruction processing, the 6 steps, we need to know fetch instruction from memory, decode, instruction, evaluate address, fetch operands from memory, execute operations, and lastly, store results. And later on, we will talk about stacks, right? Push pop on stack and how that's being used with memory. So when you compile your program, like the functions go on the stack, the variable go on the stack, your array goes on the stack, and on the low level, how does it do that? Okay, so toward, I want to say week 10, we'll talk about that. Questions?
Professor, can you give an example of number 4 again? Did you say it was like data structures or something? Oh, no. In the same list. Just.
Oh,
Yeah.
okay. Yeah, so for fetch operands from the memory, so think about like if we do like this, right? If our instruction is add R0, R1, R2, for example, right? So if our instructions start with this, it's going to take the first two steps. It looks at the add, it gets it, and then it decodes that, right? So it needs to break it down to 0 and 1s. And we will see what that means add in bits, okay? Then it's gonna look at the address, but for step 4, it's gonna handle the operands right here, okay? Because there are values that are here, right? We don't add these for no reason. You gotta have something here. Or if you're using a label here, like you do an LEA R0 and num, for example, right? It's gonna get num from the memory, and it's, you know, so it has to get what the values would be for the register 1 and 2 in order to execute, right? Because otherwise it won't be able to get the result for 6.
Okay. All right. I got it. Thank you.
Yeah, you're welcome. And assembly, you have to really visualize it on the physical level, right? For me, that's, you know, how I grasped it was I started visualizing it, and that's why we're using a simulator, so you can see how the bits, how the value go from one location to the next location, and then how it takes that and store it into a register and take that and put it into the memory. So you really have to visualize it, and eventually you would see it, right? As you look at your program, you're like, oh, it's here at this register. Now it's going to be, you know, and that instruction is going to go into the IR, and then the PC looks at, you know, the address and so on. Okay, questions? All right, so now we are going to look into more on assembly language. Okay. So all your when it process your instruction, there are only two parts that it sees. The opcode, which is the instruction, what it does, right? Operations it needs to perform. And the operands, that will be your data or your memory address, right? That could tie to a label that can be used at a certain location. So there are two things, opcode and operands. Okay. And so opcode is what it needs to do, and operands is who is it doing it to, right? Or what is it doing it to? So data and location is the operands. So now when we answer these questions, okay, we can simply include those two for number 10. The essential parts of instruction processing are two, opcode and operands. Operations for the opcode and data and locations for operands. And you will find that on page 5 of the notes. So here it talks about how the instruction is encoded in bits, just like what we talked about earlier. And it will be a fixed length, and for LC3, 16 bits. Other system, more. So CU needs to interpret the instructions. So it's going to generate signal to carry out the operation like add. or load. Now, the operation can either completely execute it or not. Okay. So the instructions and format is what we known as ISA, or instruction set architecture. So the architecture we learn, LC3, is used for ISA, instruction set architecture. Okay. And this is under the RISC architecture. Now, you would see a lot of processor that's in the market, like I mentioned in the first week. RISC architecture is also used in some of your smartphone processor, like the Android ones, like the Snapdragons, the A5, A6, that uses ARM. So the existing RISC architecture that you would see is it uses ARM, and they're different version of ARM. Okay. So you do see some similarity after you learn LC3. When you read an ARM program, you would see, right, similarities in because some of the instructions is the same, and then there's additional instructions. Okay. So now we're going to talk about 16-bit instruction in LC3. So we know that uses a word, which is 16 bits. So all your instructions is going to be 16-bit. The 4-bit in the front, right? Remember how we looked at your bits from bit 12 to bit 15? That's going to be dedicated to your opcode. Your opcode could be AND, add, load effective address, load indirect, and so on. So these front 4 bits are used for your opcode. And then the way that we have it is on your destination, that's where it's going to store the result, right? That goes next. So that will be bit 9 to 11. And then your source register is going to go, your source is going to be next, the next 3 bits. And then lastly, on the least significant bit to the bit 2, that's going to be your second source. So when you say add R1, R1, R2, right? That's what's happening. So the add is really 0, 0, 0, 1. Okay, so it turns on bit 12, and that's how it's going to know to add. And then these are going to represent certain registers. So this is just an example, as you can see. So when it sees this in the first 4 bits, it knows to add, and then that will be, you know, who is it adding? The source 1 and the source 2, and then where is it going to put in the destination register? Okay. And sometimes the source doesn't have to be a register. It can be a value, right? We can add a 0 to a certain register. We can add a decimal. We can add a hexadecimal, and so on. So in this example, we would say add R6, R6, R2. So we know that it's going to be 0, 0, 0, 1 for the first 4 bit. This is your destination. You register, that's where it's going to put the result after it adds the value from register 6 and register 2. Okay. Now, load instruction is used to read data from memory. Like you would load a label. You saw LEA already, but here it shows you the LD. So if you have a label and that label, you can fill it with a hex value. You can initialize it with the value. Then you need to load it to the register so it can operate. Okay, so it needs to read it. So when we load it, we're really reading the data that's at this label at a certain location in memory that's called label 1. Okay. Now sometimes you would see LDR, and LDR is for load for the register, right? And it's using a little different compared to the regular load, where you would have the destination, the base, and the offset. But when we write it, we would use the register, but when it loads, it actually loads the memory address. So when you see offset like this, it uses these bits from 0 to 5, that will be 6 bits, to really store it uses this for the address. So in the case where we load, we do an LDR, register 2, register 6, and register 3. What happens is it's gonna load, it's still gonna do the same thing as the other load, but instead of the values in the register, it's gonna use the address of the register 3. And then it's gonna use the base of the register 3. So I put that here. It says add the value 6 to the content of register 3 to form a memory address. So you often see LDR being used when you're loading the content from a memory location. Okay. So we load the content of that memory location to register 3. So whatever that you put at that location, okay, it's gonna go to register 2. We'll do some LD, LDI, and LDR. I often use LD and LDI more, and we will see the difference later on, why we would use some of those. Okay. So to break down the fetch step, right, it's going to load the next instruction, which is add the address that's stored in the PC from the memory into the register. So it needs to bring, right, the instruction that was at the address in PC to IR. Okay, because in IR is then it's going to be able to execute. So it needs to bring it from the program counter to the IR, the instruction register. Then what's next is it's going to copy the content of PC into your memory address register, because that's going to be the address that's going to go into the MAR. After that, it's going to read. So it's going to send a read signal or read, right? And then after it receives the signal, it's going to copy the content of the MDR into the IR. So ultimately, it has to get the content into the IR in order to operate. So first, it needs to get it from the PC counter, sends read, then it's going to copy the content from MDR, which is data, going to the IR. So after that, it's going to be able to go to the next step, which is decode. Okay, so as it brings into the IR from the PC, it needs to increment 1 up. So it needs to do a +1 because now it needs to get ready for the next instruction in the PC. Okay. That's going to be queuing the next instruction because it's already bringing in from what was in the PC into the IR. So it has to do a PC +1. So after the fetch, it's going to decode. And we talked about what the opcode is, right? So in LC3. So this is always going to be the first 4 bits of your instruction. This. And so from 4 to 16, the decoder is gonna assert your control line. So what it needs to do in the decode is you really need to make sense of what that opcode is. That's what it's doing. So depending on what you put in the opcode, it's going to be able to identify the operands and the remaining bits. So if we're using an LDR, it needs to interpret this, and it needs to make sense of, you know, addresses from register 3 and 6 and put it into. But if you're doing a regular load, like an LD, right, instead of the addresses, it's going to look at the data value. Okay, so depending on what that opcode is, it has to make sense of the opcode first, and then it's going to say, oh, that's an address that I'm using or values that I'm using from that register. So here, that's how it's able to handle the operands, which is for the next step, right? And as you see, you're going to say, oh, okay, that's how it's going to be handling the subsequent, the source registers, or, you know, the label. So for the LDR, the last 6 bits is going to be dedicated to the offset. If you're doing an add, the last 3 bits, right, it's going to be for the operand R3. And then it's going to skip 3 bits, and then in the middle, it's going to handle R1. Okay, so that's going to get it ready for the next part, which is your fetch your operands, on how it's going to treat the data or addresses, or the label at an address. So when we're using an LDR, it loads the data from the memory. So it's going to go and pull it from the memory. But if you're using an LD, it's going to get that from the register. Okay, so here, when we're using an add, it reads the data from the register file. The same thing with LD. When you're using just a regular LD, it's going to pull it from the register. Compared to the LDR, it's going to pull it from the memory, your data. And then after it has the opcode and the operands, then it can execute. So as it executes, it's gonna send operands to the ALU because we have to handle the data, and usually that's just calculation. Then it's gonna assert the add signal. So the example that we use here is a store. ST stands for store, right? So it can do nothing, or, you know, to really store the data, then it's gonna take the label, which is at a certain memory location, right? Put it into register 5. And then lastly, it needs to write the result to the register or the memory, depending on your code. Okay. So when you run a function and you return, right, this is happening. Okay. And in C, you know that you use the main function to run, even though you don't customize a function. So it's still a function that's ran. All right. So there's additional example on how it stores or write to the memory. So it needs to add the result to the register. Remember, the computer only adds, so it takes that value and it puts it into the register by adding. And then it's also placing that onto the destination register. So that's how it can store your data to the memory. So with that, it puts it writes the address to the memory address, and MAR only handles address. Remember that, where the data is going to be with the MDR. And so in storing result, it has to do the right signal. That's how it's able to store to RAM or register, but usually RAM. Okay, any question with this? I know it's a lot, right? I know that you know a lot of this because most of you took C++, and the first couple chapters, it talks about processor, data, bytes, data type, and all of that. Right? You already been using this all this time when you write your program. It's just now that we bring it to the lower level so you can understand it a little deeper. Okay, so let's give it a try for number 11. Describe how instructions is fetched in the instruction processing, and you can include what's in the notes there. I'm fine with that, but as you do it, you need to understand it. It's important. Instead of just copy and pasting, we need to understand it. So it loads instruction, right, at the address stored in the PC. We set up, it needs to bring that in from the program counter into the IR, and then it's going to need to load the content of the PC into the MIR, right? It's always going to have the address from the PC. After that, it's going to send the read signal, read the content of the MDR because that's where the data is, and store it into the IR so it can use that data to operate, which is the next, or decode, which is before the operation. Then after it brings into the IR, now the PC counter needs to go +1, up 1, so that way it can be ready for the next instruction. And when you take operating system class, they do talk about this at the higher level, right? When you're looking at processes on how, if you, let's say you learn Windows operating system, it talks about processing queue and how it's able to use, like, to queue what's next or come back to a certain process. Any question with 11? For 12, we said that control instruction should be used when we want to change the sequence of instructions or follow instructions to execute, such as loop conditions, right? Hence the term control statement. So you can control how your program is executed. And at the low level, we can jump, which is JMP, or we can branch. Negative is the baby n. BRN is branch for negative when it is a negative value. Branch when it's 0. Branch when it is positive. And that's how we implement loops and conditions. So where do I find that? Right here on page 7. And I bolded it for you. So right before it says, what if we don't want to always execute the instruction following this one? So it's going to go top down, right? Line by line. But what if halfway through, you have a section where you don't want to execute yet, right? We can jump. We can jump to a label. And with that, what will happen is it's going to use that label, and that label is at an address. And at that address, it's going to have a different set of instruction later in your program. So when you send it to a label, basically, right, that's at a different location in the memory where it has the subsequent instructions. So then when you jump, what happens is the PC, right, has to go to that section. It gotta have that address and then take that address, put it into the IR, take the data, put it into the MDR, and that's how it's able to execute the next part of your program when you jump. Okay. And at the high level, you would see like something like break and continue, or you can send to a label. I know C++ does that, and so is Java. Okay. Because I covered that when I taught those classes. So here you would find, some example there. So we can say jump to label 2, and we might have, right, label 2 a little bit further down in our code than we would have label 2. Add R1, R1, R2. So that would send the PC to contain in the register, and then it will have the address of the next instruction to fetch, which is for this part. Okay. Any question regarding control unit and change sequence? And when you loop, right, you're not going to the next line. You're going to come back to the prior lines, right, to be able to keep going for a while, right? In the case where if we're doing a while loop, and if it's infinitely while, it's just going to keep going. So it's going to keep coming back to the prior lines, and it's just going to keep doing that. So you are changing the sequence of your program. When you're doing a for loop, same thing, right? Until it gets to when it counts down to 0, right? Or when it increments up to a certain value, I can count up, or when I'm doing an increment up. So I can go up 5 times, and then it's going to come back to the next part of the program. So you're changing how the sequence would be. Instead of top down, it's going to move around in different parts in your program. So jump and branch. So when you're doing a jump, and we'll expand more on jump and branch also in the future chapters, but this gives you the overview. So a jump, you would get a 1100 in the first 4 bits here. Okay. And when it jumps, it's going to be the base, which is usually just a label, and that label is tied to an address. When you fill it with an address. Okay, so this example, it shows you how when you're loading content to register 3. Okay, so if you're a diagram person, you can use this to visualize how content of register 3 is loaded to the PC. And this depicts the entire process where it would fetch, decode, and then execute. So here I highlighted this section. It says the control unit will repeat the instruction processing sequence as long as the clock is running. Okay, so if not processing instruction from your application, then it needs to process instruction from your OS, whichever OS you're running, whether Mac OS, Linux, Windows. So because OS ultimately is a program, and that, on operating system, it is expanded to managing processor and resources. Therefore, we're able to look at, your tasks, your processors, processes, especially if you do Control Delete Task Manager. Okay. And then also managing files and resources, devices, and so on. So to really stop the computer, we would need to AND the clock generator with a 0. Remember, when we AND something with a 0, it is 0. And so when the control unit stopped the clock signal, it stopped processing. So when we wanted to stop process, we would, at the low level, that will be an AND 0. And so when you look at your program, when you're doing a halt, okay, what does that really mean? Stop execution, right? So here, this diagram depicts the clock generator, and this is the AND gate. Okay. So when it runs, when you AND it, and then you add the 0 with the AND, then your clock stops. Any question? So for 13, we can say that we can stop processing by ANDing clock generator signal with a 0, and the control unit stops seeing the clock signal, so therefore it stops processing. Okay, any question? So that pretty much covers chapter 4. I encourage you to go back and read the chapter or look at the notes again, look at your assignment again, understanding the questions and also the processes and all the components, and also von Neumann model, because a lot of these will come up not just for your exam, but I think, it's going to come up on other classes, other computer science classes. And, if you understand the foundation of the system, you can do a lot to the system, right? Fortunately for me, I started learning hardware first, so I'm really strong in hardware and I can understand the concept in hardware. And then I also had extensive classes with OSs, and that really gives me a an expanded understanding of how, system resources are being managed. So as you take those classes, really try to integrate the concept that you learn. And all of these classes bringing in concept, and ultimately you would understand the complete picture. These are little pieces of puzzle, and eventually you will have the big picture. So every class that you're going to get, whether it's programming or architecture class or digital class and so on, or OS classes, it's going to give you a little bit more understanding of what your system does and why you're writing the program a certain way, because ultimately we're working with resources like RAM, temporary storage, and how the processor sees things. That's it. Okay. I have a chat question. Do you know outside resources to visualize more, like animation, or still show step by step? I think that I haven't really looked at some of the resources for assembly. You might be able to find tutorials, that would be for other assembly language. LC3 is limited in general. Like most universities, you don't see there are a few TAs that made tutorial videos, but when you start seeking, I don't know, I've been looking for some videos from before, and I've had students that reached out to me from overseas, from other states, that they've been taken and they've seen my lecture, and they've asked for, some resources. So as far as animation and things goes, I haven't seen that, but if I do find it, I will share it with you. You might be able to find some stuff on ARM, but most people who teaches this or provide tutorial, usually, it's pretty cut and dry. So, so you're gonna get, the concept, the diagrams, the things that at the 2D level, nothing fancy. That might be a need. So down the line, if you want to build something that is easy for the user to absorb and understand. Computer science, there's a lot of abstract concept. So you have to get really the deeper understanding to really understand those concepts. And, it is a tough field to really expand on. But however, once you, learn this concept and understood it, things are going to make a lot more sense. And of course, if you are not clear on something, you can address it with me. And if I can help you visualize it in any way or re-explain it to you in a different way, I will try to do that. Okay. But, as we learn this, and hopefully when you apply it in your lab, you can see it. I've had students that know nothing about LC3, and by the end, they've written 150 lines in LC3 for their project and understood everything and understood assembly. So this has proven to work for a few years now. So I hope that as you move along in this class, it will be easier, right? The concept will be clearer. And as you practice and have more hands-on, it will make more sense. Okay. I do too, because I do wish for you to be successful, right? I'm in this business to make sure that you are ready and you understand and you can be successful. I'm not in this business I'm not in my role to make things more difficult for you. It's just, topics sometimes can be challenging. And this is one of the harder class at community college level. But I have faith, and with this, I encourage you to read, right? To go back and study. It's one of those things that you have to also practice, because learning it once doesn't always mean that we can be an expert, right? So we have to keep on practicing, just like programming in C++ and Java and other languages as well. So, and if you read it once, sometime you forget. So, you have to revisit the topic. And I'm forgetful sometimes too. Sometimes I have to brush myself up with things that I have learned a while ago. And then, to kind of keep up with things. So, okay. All right. So with that, we can submit our assignment for today. And since I have a little bit of time, let me open up the lab and I'll give you a little bit of preview. Okay. Let's see. I think I have a new version because I edit it every so often. So last year, I edited because I've taught this class on campus the prior years. And then when COVID hit, we went online and I did Zoom like your group now. But as I move along, I added some stuff, as you can see. So you are going to work with additional opcode. We've done LEA and some of the simple ones, but you are going to load and store in this upcoming lab, and I will walk you through it, right? And these programs are really, really short, so it's no big deal, but we will have to understand what we're writing, and then we are going to apply algebraic equation to our program, because most of you have taken math courses, and so it will be easier to really understand it from a variable level, and then how you use those variables as labels, okay? And those labels are at a certain location. So we will work on these, okay? And then for the later part, we are going to write a longer program. And this is going to show you how you can do comparison. So when you write a comparison or you're using comparison operators in C++, Java, Python, JavaScript, etc., right? But for example, C, what is it really, at the low level? Okay, so I want you to be able to see on how you can write a function to compare values. Okay, and so we're going to do that one. Okay, so let's say if X is greater than Y, then do this. If it's less than Y, then do this. So with that, we also apply conditions and we can branch it, right? We can send it to a certain area and so on. So we will explain, we will work on that program, and that will be the lab. So it's a little bit different than what you've seen. Okay. Logic and Computer Design Fundamental by Mano Kime is a good source to build your background. Yep, that's also a good book to use. There are other books that is used for architecture. I think Cal State San Bernardino used a book specifically for ISA. The expectation also, with learning that book is also a little bit more advanced. So you can also search for architecture and design book or logic and design book. That also helps you. But, this book gives you like the basic level. You should understand. They break it down to what a control unit is, an ALU is, and grasping that, and then reading additional advanced book is also going to build your knowledge. Okay. So also, in a couple of weeks on one of the lab days, I have to present at board on the 15th of March. I will have a pre-recorded video ready for you. And then I will be available during office hours in case you have issues. But, I hate to do that, but I can't get out of it. They have asked me to present. So, and I have submitted my presentation. So I will remind you so that day you will not have to meet live. You simply can, watch the video and work on your lab. And then I will address some of your questions when we return the following week. Okay. Oh, thank you. Yeah, it's just to kind of showcase some of the programs and things. So we have apprenticeship and other things that are going, but thank you. All right, let me stop recording